Okay, hi guys. So in this lecture, we'll be continuing on seeing more on Gibbs free energy. So let's get started with an example. So we have H plus aqueous reacting with OH minus aqueous and forming H2OL. Okay, so delta R G naught for this reaction can be written as delta F G naught H2OL minus delta F G naught H plus aqueous minus delta F G naught OH minus aqueous. Okay, so where H plus aqueous is a reference ion, so we can write that delta Rg naught for the reaction can be written as delta Fg naught H2OL minus delta Fg naught OH minus aqueous. Okay, or in other words, we'll be considering delta Rg naught for H plus to be 0. Okay, next example is we have HCl aqueous giving us H plus aqueous and Cl minus aqueous. So again we can write that delta Rg naught can be written as delta Fg naught H plus aqueous minus or rather plus delta F G naught delta F G naught Cl minus and Cl minus aqueous minus delta F G naught HCl aqueous. Again delta G naught for H plus aqueous would be considered 0, and we can here with, if we know the delta Rg naught for the reaction, we can calculate the Gibbs energy of formation of Cl minus aqueous from delta Rg naught minus delta Fg naught HCl aqueous. Okay, and just note here that delta F G naught for O2G would be considered 0, delta F G naught for Br2L would be considered 0, and delta F G naught for gold in solid phase would be considered 0, but delta F G naught for carbon in graphite form would be considered 0, and delta G naught for carbon in diamond form would not be considered 0. Okay, we also know that delta R G is equals to delta RH minus T delta RS. Okay, so at 300 Kelvin we can write that delta R G300 is equals to delta R G300 minus rather delta H300 minus temperature is 300 Kelvin times delta R S300. Okay, and similarly what would be at 310 K means the value of delta Rg we have been given delta R H300, delta R S300 and CPM at the temperature. Okay, so we can write delta R H2 minus delta R H1 would be equals to delta R CPM T2 minus T1, assuming that the CPM is temperature independent, so T2 is 310 and T1 would be 300. So similarly we can write delta R S2 minus delta R S1S delta R CPM, and also we are giving that we are using this reaction is at constant pressure. Hence, as this is at constant pressure which is already given in the reaction, we can write delta R S2 minus delta R S1 would be QP, and QP can be written as delta R CPM ln T2 upon T1. Okay, so similarly we can write delta R G300 10 minus delta R G300 can be written as let's say first delta, how can delta RG300 be written as? Delta RG300 can be written as delta R S310, or this is 310, sorry, minus 310 delta R S310. Okay, so if delta R CPM is equals to 0, or in other words we can say that delta RH and delta RS both are temperature independent from T1 to T2, then we can write that delta R 310 would be equals to delta R 300, delta R H300, and delta R S310 would be equals to delta R S300. Okay, or in other words we can write delta R G310 would be equals to delta R H300 just 300, because delta RH 310 would be equals to delta RH 300, so it would be minus what is the temperature is 310 and delta RS 300. Ideally it should be 310, but as 300 delta RS 300 is equals to delta RS 300, so we are directly putting the value of delta RS 300. Okay, now let's say what happens in case of chemical reactions or phase transformations. So for chemical reactions, oblique phase transformations, we can write delta S system plus delta S surrounding is equals to delta S total, and we can also write that delta S system minus delta H system by T is equals to delta S total. Okay, as delta S surrounding can be written as delta H system by T, because the heat is released by the system to the surrounding at constant pressure. So this would be T multiplied by delta S system minus delta H system would be equals to T times delta S total. Okay, so at constant temperature and pressure we can write that this would be nothing but delta H system minus rather I'm just using this here, and minus T delta S system would be equals to minus T delta S total. Okay, and delta S system minus T delta H S system would be nothing but change in Gibbs energy of the system at constant temperature and pressure would be equals to minus T delta S total. This is a very important relation. Okay, so now for an spontaneous or irreversible process, we can write that delta G of system temperature and pressure at a particular temperature and pressure would always be negative. Okay, so as delta S of system or entropy of the system increases in a spontaneous process, this implies that delta G would be going more and more negative. Okay, and for a reversible process, or equilibrium reaction which is at equilibrium, we can write that delta G of system at a particular temperature and pressure would be equals to 0. Okay, and for non-spontaneous process, we can write that delta G of system at a temperature and pressure would be greater than 0. Okay, so if we draw the graph of the Gibbs energy with particular temperature and pressure, so this is Gibbs energy, we will see that it has a nature like this, and at here we have equilibrium state. So at equilibrium, delta Rg at a particular temperature and pressure would be equals to 0. Okay, and this is minimum. Okay, so when a reaction takes place in a closed vessel at constant temperature and pressure, Gibbs energy of system decreases and attain minimum value at equilibrium. Okay, so we can write here that when a reaction takes place in a closed vessel, so after this point you can see that it goes to a constant value, so delta G would then be 0. This is the graph between Gibbs energy or G. Okay, so delta G would, as you can see, is having a downward or negative slope, so delta G would be decreasing. Okay, so when a reaction, delta G would be negative and the graph would be decreasing of decreasing nature. So when a reaction takes place in a closed vessel at constant temperature and pressure, Gibbs energy of system decreases. By the way, this is with respect to time. Decreases and attain minimum value at equilibrium. Okay, so if the reaction also takes place in or at non-standard state, then at equilibrium we can say. So suppose if reaction takes place at non-standard state, then at equilibrium we can say that delta Rg at temperature and pressure would be equals to 0. This is only valid at equilibrium. Okay, and if reaction takes place at standard states, then at equilibrium we can say that delta R G naught at temperature and pressure would be equals to 0. Okay, so at constant temperature pressure, chemical reactions are spontaneous in the direction of decreasing Gibbs energy. So with that note, we come to the end of this lecture. In the next lecture we'll be seeing more on Gibbs energy. So till then, good luck and goodbye.